Hello, Chem 1. In Unit 9, we've talked a lot about the different types of chemical reactions. Today, we're going to talk about energy and entropy, topics from first semester, and apply them to these chemical reactions. Let's get started. One of the questions we're going to try to answer today is, why do reactions take place, or what seems to be a driving force behind these reactions? To start, let's talk about the difference between spontaneous or non-spontaneous reactions. Spontaneous reactions are typically initiated and then will continue on by themselves without intervention. A match is a good example of this. We give it a little activation energy, and then as it starts to burn, it will continue to burn as long as it has fuel without us adding more and more heat to it. A non-spontaneous reaction is something that you have to constantly intervene with. Baking a cake would be an example. When you bake a cake, that's a chemical reaction, and you have to continually add heat so the cake continues to chemically react. In order for something to be spontaneous, the energy or entropy change must be favorable. Let's first focus on energy. Typically, when we think about energy changes, we think in terms of endothermic and exothermic. We know that endothermic reactions require energy. Energy is going to go into the system from the surroundings, and therefore the reactant side will have more energy than the products. The enthalpy change, or the delta H, will be positive because the system is gaining energy. Energy is going into the system. Typically, these reactions and the surroundings will feel cold. If you touch a test tube where an endothermic reaction is taking place, the test tube is going to feel cold because the reaction inside the test tube is absorbing heat into the reaction from the test tube. There are physical endothermic phase changes: melting, sublimation, vaporization. We've talked about these in earlier sections. This graphic down here can be really helpful. It shows that an endothermic reaction, the system, this would be the actual chemicals involved, they're gaining heat from an outside surrounding location. Therefore, the surroundings are going to get colder. Exothermic would be pretty much all the opposite. Exothermic reactions are going to produce energy. They're going to give off energy to the surroundings, and therefore the surroundings are going to get warmer. The reactants are going to have less energy than the products because the reactants are going to lose energy, and therefore the enthalpy change, delta H, is negative. The heat term will be on the product side because heat is being produced. And physical examples of this would be freezing, condensation, and deposition. We can see down here in our exothermic model, the system, or the chemicals involved, are going to lose heat to the outside surroundings, and therefore the surroundings are going to get warmer because that's where the heat is going. So just remember, endothermic, heat is entering the system; exothermic, heat is exiting the system. Most reactions, no matter if they're exothermic or endothermic, are going to require some type of activation energy. Activation energy is just the energy to kind of start the reaction. A lot of times we'll see graphs that demonstrate activation energy. Let's say we have an exothermic reaction. An exothermic reaction is going to lose heat, which means the products are going to have less energy available than the reactants. A good example of this would be a match. A match has a certain amount of stored energy. In order to get that stored energy to start reacting, we need to add a little more heat, sometimes through friction. And if we can get enough heat, then this reaction will spontaneously happen and the products will lose heat to the surroundings, therefore being exothermic. So this distance right here, that is the activation energy, the energy required to get that match started. In an endothermic reaction, heat is entering the system. So we have our reactants, and our products are going to have more stored energy, endothermic. In this case, the activation energy you can see is much larger, and it's because we've got to get over a much larger hill in order for this reaction to spontaneously occur. A good example of this would be a cold pack that you break and the chemicals mix and it starts absorbing heat from the surroundings. We learned in a previous unit that matter tends toward low energy. Matter typically wants to break apart so that it has lower energy molecules with not as many bonds. So because of this, we would assume that exothermic reactions where the products have lower energy are more favorable. Another thing that can drive a reaction is entropy changes. For review, entropy is the degree of disorder or chaos within a system. Solids have particles that are fairly organized, so entropy would be very low, where gases have lots of disorder within them, and therefore entropy would be very high. We know that matter tends toward high entropy. Naturally, chemicals and reactions tend toward more disorder. not becoming more organized. And therefore, any reaction that would create more disorder would be considered favorable. When you're looking at these reactions, the easiest way to see if entropy is increasing or decreasing is to look at the moles of gas. So if you're creating more moles of gas, then entropy is increasing. If you're creating fewer moles of gas, then entropy is decreasing. We show entropy as a delta S. S is the term used for entropy. And we would just put delta S next to the reaction to show what entropy was doing. Other things to remember: solids dissolving will always be an increase in entropy because that solid, which is very organized, is becoming more disorganized in an aqueous solution. A gas dissolving, though, will decrease entropy. Gases have high entropy, and if we put them into a liquid or confine them, that would lower the amount of entropy or increase organization. Temperature can also affect entropy. If you heat something up, molecules are going to move faster, and therefore entropy is going to increase. And if we cool something down, molecules are going to come together and maybe be more organized if they crystallize and decrease entropy. Let's take a look at some examples here. If we organize a silverware drawer, that is lowering the entropy. It's becoming more organized. So that's a decrease in entropy. If we dissolve sugar in tea, dissolving a solid in a liquid is going to decrystallize that solid and create higher levels of entropy. If we melt an ice cube, that's going from a solid to a liquid. Entropy is increasing. And then crystallization, that's going from a vapor to a solid. Gases are very disorganized, solids are not. So that would be a decrease in entropy. So now let's take a look at this on the chemical level. If we look at this chemical equation here, we have H2O liquid going to H2O solid. That is becoming more organized, and therefore that should be a decrease in entropy. If we look at this one, we're going from a liquid to a gas. Gases have high entropy, therefore more disorder, increase in entropy. This one we have solid NaCl, and then we have aqueous NaCl. This equation is telling us that we are dissolving the salt. Dissolving solids is an increase in entropy. In this case, we're dissolving a gas. We have carbon dioxide, and we're putting it into an aqueous solution. Soda would be a good example of this. The CO2 in the gas form will have more chaos or more disorder than in the dissolved form. Therefore, we are decreasing entropy. Anytime you have a decrease in temperature, molecules are going to slow down and become more organized. That's a decrease. All right, now let's look at some chemical reactions. If we look here, we have 2 moles of gas, 2 moles of SO3. And then on the right side of the equation, we have 1, 2, and then 1 mole of O2. So we went from 2 moles of gas to 3 moles of gas. We are increasing the number of moles of gas, and therefore we should be increasing the disorder. Entropy increases. In this next one, we're starting off with 1 mole of solid, and we're ending with 1 mole of solid and 1.5 moles of gas. So we went from one thing to 2 things. Entropy is increasing. In this next one, we have 2 moles of gas of hydrogen, 1 mole of gas of oxygen, and it's becoming 2 moles of liquid. So we're going from 3 down to 2, and it's going from gas to liquid. Entropy is definitely decreasing. Here's a combustion equation. We have 2 moles of liquid octane and 25 moles of oxygen gas, but it produces 16 and 18 moles of carbon dioxide and H2O, which would be a total of 34. We are going from roughly 27 moles to 34 moles. We have more disorder as we move to the right. More gas is produced. This one down here at the bottom is a little tricky. We have 1 mole of hydrogen and 1 mole of chlorine, and we're producing 2 moles of HCl, and they're gases all the way across. We start with 2 moles of gas, we end with 2 moles of gas, which means entropy stays the same. It doesn't change. It's just 2 and 2. It's really important that you know how energy and entropy affect chemical reactions and which types of energy and entropy are favorable when we look at chemical reactions. Take a look at some more examples in the activity. Let me know if you have questions. We'll see you soon.